This video shows the Requs forecast function. It's the only part of Requs that is used after the code is written. It does forecasting of failure data. The very first step is to enter or import the failure data. You can get this from Jira and other defect tracking programs. You can do a couple of different things here. You can see we have the date. We have the number of hours that were spent testing on that day. We have the total number of defects found that day, as well as the total number that were critical. Obviously, the fourth column has to be less than the third column. We can't have more critical defects than there are total defects. And so we can enter this data in during development and testing. This data needs to be refreshed fairly regularly as the testing is ongoing. So here we have the inputs. Then we have the results, which are updated incrementally as well as testing is ongoing. You can see it predicts the estimated defects, so it forecasts them. The machine learning models under the prediction tab predict the total defects without any failure data based on empirical data. This forecaster is taking our actual unique defects and just simply trending forward. And there's a few models that it uses to do that. The exponential model assumes defects are being discovered less over time in a linear trajectory. The Weibull model makes almost no assumptions. And the Raleigh model assumes that defects are found, some obvious ones are found earlier, and the edge cases are found later. The logarithmic model assumes that defects are found, that they decrease over time, but non-linearly. And the actual cumulative is just simply summing up the cumulative failures and cumulative hours. Okay, the first thing we want to do is let's look at our fault intensity versus usage hours. Fault intensity is just simply the unique defects divided by the usage hours, and the cumulative unique defects divided by cumulative usage hours. You can see the blue is the total fault intensity and the red is the critical fault intensity. Now, if we look here, the first data point is way out here to the right. So initially the fault intensity was 0.175. Now it's down to about 0.519. So clearly the defect discovery rate is going down. That is good sign number one. That's one of the first things we want to look for in making a release decision. Now, just because it's going down doesn't mean it's good. It just means it's not terrible. So we need to look at other data. Another way to look at it is the non-cumulative faults over time. It's just a different way of seeing the same data. We can see this curve here. It means that things are leveling off. Now, what we'd really like to see is that they're actually flattening out, which is not happening yet, but we can see that it's starting to level out. So that's a good sign. All right, let's look at each of the models. This is the exponential model. It graphs through the fault intensity bubbles. So each one of those bubbles was a day of testing. It computes the total defects largely from this line. The DRE is the defect removal efficiency. So it's estimating that we're about 65% of the way through finding all of them. The growth rate is related to the slope of that line. And you can see it's estimating a total of about 129 defects. Now, the fractional value there is the fact that it's an estimate. We keep it fractional to make it clear. That's an estimate. This is an actual. We found 84. It's estimating about 129. That would put us at about 65% of the way through the exponential model. The Weibull model doesn't have the same constrictions as the exponential model, and it's estimating 89 defects because it is equipped to handle the slowdown, the non-linear reduction in defects. So this model was able to handle that better than the exponential model. So it's coming up with about 89 total defects. And then the logarithmic model, it's determined by, it uses a logarithmic graph to get those intercepts. And the logarithmic model does not predict the total inherent defects because it assumes it's infinite. What it does is basically forecast how close we are to getting to that point of which there's virtually no defects left. And then the Raleigh model, this particular graph, we have one model here that simply doesn't work for our data. The Raleigh model assumes that the defects are going up and then coming down, which clearly our data is not doing. Our data is going straight down. So just from looking at this, we don't really want to pay attention to the Raleigh model. The Raleigh model is predicting 2.6 total defects. Clearly, we already found 84, so this model can be thrown from the mix. Now let's look at our actual cumulative. We found 84 so far. The actual cumulative time between failure is a little over 19. The total critical defects is 48. The time between critical defects is not quite 39. And so our critical failure rate and our non-critical failure rate are shown here. So the average cumulative tends to be conservative because it's taken into account the early part of testing where more defects are being found. So if we look here, we'll see these estimates are more, with the exception of the Raleigh model, these are much less conservative, which is what we would expect because the software is actually getting better as it's going through testing. So now let's look at forecasting. We can pick any of our valid models. We don't want to pick the Raleigh because we know that one's not the right model, but we can look at the other ones. Let's look at the exponential model. We can forecast two things: the additional test hours and what would happen. Let's say if we had more test hours than what we have. Maybe today is not the end of testing. Maybe we have 1,000 extra hours left. We can forecast what the failure rate will be, or the MTTF, actually at that time. So in this particular case, if we get about 1,000 more test hours, the MTTF currently now is down here at around 40. It would actually go up to around 113 if we had about 1,000 more test hours, assuming that the defects are removed along the way. We could also forecast the defects and how many of them we fix. So finding and fixing defects will have an effect as well. So let's look at the graph on the right. You can see as I click this slider, the forecast is going up. What if we fix, now we currently have 84 defects. The model was predicting around 129. What if we fix 25 more? Let's just make it real simple. Right now, our mean time to failure is here. If we fix 25 more defects, we would be at around 50 hours MTBF. So it's two different ways of looking at it. Some people like to focus on fixing defects. It's more tangible. Test hours, some people feel uncomfortable with because you could have superficial testing and rack up a lot of test hours, and you could test the same thing over and over again and not get growth. So we have two different alternatives. We could do the same thing with the other two models as well. The release decision comes with basic three parts. One, is our fault intensity going down? If it's not, we stop right here. If the fault intensity is increasing, the other metrics honestly do not matter. Right now our fault intensity is going down. That's a good sign, but that doesn't mean the software is ready to release. So that's a good sign. We got past the first gate. The second gate is, what are the models telling us? Let's exclude the Raleigh model because it's not the right model for our data. Let's look at the exponential and Weibull and logarithmic. And let's look at the estimated mean time to failures at those models. We would compare these. Actually, we could create a band of these three models, low, medium, and high, and take a look at what's our goal for this software. Let's say it's 100 hours. Do any of our models actually estimate 100 hours? And the answer is one of them does. If our goal was 50, then we've got one that's very close to estimating that right now. So next we take a look at our models. Is our goal anywhere in the bounds of what these models are showing? And then finally, the very last thing we look at is, assuming we're not done with testing yet, is there any hope we'll meet the objective by fixing defects and testing longer? So that's something we need to look at there. Is the release decision many times isn't a simple yes or no. Many times it's conditional. If we're very close to meeting the goal but not quite there, it could be the release could be conditional on fixing X number of defects or running X number more tests. So basically, that's how we use the actual failure data to forecast out and make release decisions. Another thing that we'd want to do as well is go back to our predictions, which did not use any data at all, any failure data. It used empirical data from other programs. We should also compare what the predictions came up with versus what the trend is showing. That allows us to continually make a more accurate prediction.